So we just looked at the copper zinc half cells and combined them to make an electrochemical cell. We found on the voltmeter that it had a voltage of 1.06 volts, which is very encouraging because it's really close to what we'd expect. What's really good about it is we got that close even though we didn't do it under standard conditions. It wasn't 25 degrees Celsius in here. The solutions we used were not 1 mole per litre. It probably is about 1 atmosphere pressure in here. And the electrodes we used were pure substances, so those things were correct. We can actually predict what the voltage of a cell will be if we know what its half cells are, using things called standard electrode potentials. You'll see them having a symbol E with a little degrees symbol next to it. You'll hear me say E naught, because it's just the way I phrase it. The naught technically should have a line through it as well, so it can be this or this. Okay. The unit is the volt because we're looking at potentials, electric potential. The physicists will tell you that that is what voltage is. It's the potential, electrical potential of something. So it's, I believe, joules per coulomb. Right? It's the amount of energy per coulomb of charge that is present. It has very little to do with current at all. And the cell that we made has got nearly no current at all. It wouldn't actually light up a lamp because it wouldn't give enough power. It has enough voltage, but not enough power in it. Okay, so what are these standard electrode potential thingies? They're numbers you're going to be given in your assessments. They're numbers you can find in tables online, tables in books called data books. So you're given them, but you need to know what they mean. You need to know why, when you make a cell, you don't get the number you calculate to get. Or very rarely will you. It'll be just a bit out, like the one we did today was out by 0.04 volts. Doesn't sound a big deal, but it is a bit out. So what are they? Well, first we need to know what standard conditions are, and these are the big things that you might need to discuss as to why your value isn't the same as the calculated value. Did you do it at 25 degrees Celsius? Probably not, because that's a temperature that puts students to sleep. Did you do it at 1 atmosphere? Probably, because we're pretty close to sea level here. Did you use 1 mole per litre solutions? Yes, you did, to start with, probably, because that's what we're likely to give you in an assessment. But did they stay at 1 mole per litre? No, because as the cell operates, that will change. So you might see a small change in voltage if you leave it set up for a long time. Were your substances, so basically your electrodes, pure? Yes, because you'll probably sand them off to get any impurities off them before you use them, which is what I did today with these ones. Okay, what are they? Well, they're measured against the H plus H2 half cell. Just like temperature is measured against the boiling and melting point of water, when we use degrees Celsius, these are saying, well, let's say that this one has a 0 voltage. It's the standard cell, what we call the standard cell. And we'll make that the oxidation cell, so it's the anode. We'll make everything else the cathode, and we'll see what the voltage is. That voltage that we get is its standard electrode potential. But because we are always putting the other half cell on the reduction side, the cathode, then we sometimes call these reduction potentials, and that's a really good way to look at it. So if I look at a data table for what we did, the copper reduction potential, or electrode potential, is 0.34 volts. The zinc one is negative 0.76. Now the fact that it's negative means that when we plug it in with the hydrogen cell, actually this reaction doesn't happen. It's not spontaneous. Instead what happens is the zinc ends up turning into zinc 2+, and the hydrogen undergoes reduction. So this becomes the anode. So if you see a negative value, it means that that substance is more likely to be oxidized. If you see a positive value, that substance is more likely to be reduced. So in this case, actually zinc is more likely to become zinc 2+, so it's more likely to be the anode. And that's what we saw in our cell that we've set up. If I'd set it up back to front, the voltmeter would have said negative 1 point something volts. And I would have just known I had it set up back to front. That's all that means. So, the little rule that we have here is that the E naught of our cell, so our completed cell, our zinc half cell plus our copper half cell, is equal to the electrode potential of the cathode minus the electrode potential for the anode. We don't change any signs or anything, we just put those values in as they are. So in the one we've got here, this means the E naught for our cell, in theory, so if it was at 1 atmosphere, 298 Kelvin, and 1 multi-litre solutions, would be, here's our cathode, so 0.34 volts, minus, here's our anode, negative 0.76 volts, minus and negative, of course, is adding, so my mind is saying that is positive 1.10 volts. Now on my voltmeter sitting in front of me, it says 1.06 volts, which is a little bit lower. But there are reasons for that. One is that we're not using 1 multi-litre solutions, so that does have an effect. Another one, it's not 298 Kelvin, 25 degrees Celsius. So those do have an effect on it. All right? The voltage number itself, just to be a bit of a warning, the voltage number itself doesn't mean how quickly the reaction goes. It's not about the rate of reaction. It's about whether the reaction is spontaneous or not. If it's positive, which it is in this case, it is spontaneous. If it's negative, it actually means the opposite is happening. It's not spontaneous. So you'll see examples in assessments where the answer adds up to a negative number. That just means that you're getting the opposite to the way it's drawn. They've drawn the anode on the right-hand side rather than the left-hand side. That's all. To put it simply, if you can get your head around how to draw cell diagrams for what you see, if you can calculate electrode potentials for a cell, then you're over halfway there to what you're going to be assessed against. All right. What you also need to be able to do is to link those to what you'd observe happening in each half cell if you left it going for long enough. So link it to those redox pairs we learned about last week. And shortly we're going to learn how to use electrode potentials to work out which one's the strongest oxidant, which one's the weakest oxidant, and to rank 3 or 4 or 5 of them in order of oxidation strength. All right.